In this video, we're going to develop a couple of examples of quotient rings, both of which have very different properties. For both of these examples, we're going to start with the ring R equals the ring of polynomials on the real numbers. So this is the ring of polynomials over R. Okay, so in other words, that's the set of all polynomials that can be written in the form a0 plus a1x plus a2x squared, etc., up to an x to the n, where a0, a1 through an are real numbers, and n is a whole number. All right, so that's the ring we're going to be starting in. But now we're going to define a couple of different ideals of R, and we're going to see what happens when we take the quotient of R bracket x by each ideal. So let's begin with this one. Let's say I is the ideal generated by x squared. So this is the set of all polynomials, p of x in R bracket x. Okay, so this represents a polynomial. And traditionally, when we talk about a polynomial, we use this notation p of x rather than just p. So p of x is in R bracket x such that x squared divides p of x. Okay, so in other words, p of x has to be expressible in the form x squared times some polynomial which means that really when we expand it out and write it in standard notation, we get something like this. X to the n plus 2. Okay, so in other words, it's the set of all polynomials whose zeroth coefficient and first coefficient, in other words, the constant coefficient and the linear coefficient are both 0. Okay, so that's what we're going to mod out by. We know that this is an ideal because we proved at one point that the set of all multiples of a ring element, at least in a commutative ring, is an ideal. So this is called a principal ideal. And it's the principal ideal generated by x squared. Okay, so what is R bracket I? And there's not going to be an easy way to answer this question. We don't have a whole lot of examples of rings at hand where we can say, oh, that's isomorphic to this. But we're just going to learn a little bit about its properties. So what can we say about it? Well, let's start by doing a little bit of arithmetic within this quotient ring. So again, just as a reminder, in a quotient ring, every element is a coset of I, an additive coset of I. So for example, we might have something like, I don't know, 4 plus 5x plus x squared plus I. Okay, but one thing we're going to use here, we're going to use a fact that's going to help us to study the elements of this ring a little bit more carefully. And that is the fact that this belongs to I. So I can actually write this as 4 plus 5x plus I without the x squared because x squared belongs to I. Another way of thinking of this is that these two cosets are the same because 4 plus 5x plus x squared is congruent to 4 plus 5x mod I. And the reason that's true is because this thing being added here, x squared, belongs to the ideal. Okay, so because those polynomials are congruent mod I, that means that their cosets are the same. So these two things here, this thing, this coset, and this coset, they're the same element of R mod I. All right, a corollary of that kind of thinking is that if I write down any polynomial, a0 plus a1x plus a2x squared plus a3x cubed, and so on up to an x to the n, where n is some whole number, and I construct the coset of that, well, that's an element of R mod I. But is it expressible in some nicer way? Like, for example, when we talked about arithmetic mod 12, we never needed to talk about any number bigger than 12. Like we'd say, oh, 15, but 15 is congruent to 3 mod 12. So anytime we were thinking of 15, we referred to it as 3. So I'm wondering if some kind of similar language trick could be used here. So we have this polynomial, but is there some easier way to refer to it? And the answer is absolutely there is, because everything here, assuming that these powers are in increasing order, everything here belongs to I, because I can write that as x squared times a2 plus a3x, and so on, an x to the n minus 2. All right, So all of that is a multiple of x squared, and therefore everything in the box belongs to I. And therefore I can say that this whole polynomial here, a0 plus a1x plus etc. up to an x to the n, that's actually congruent to a0 plus a1x full stop mod I. All right, so that means that this coset here, this element of R mod I, is really the same element as a0 plus a1x plus I. Okay, if we're talking in terms of congruence classes, we could say that this polynomial's congruence class is really the same as this polynomial's congruence class. So what that should suggest to us is that every polynomial is represented or representable in this quotient ring as something linear, because all of the quadratic stuff, all the cubic stuff, all the higher degree stuff goes away. It's part of I, and therefore can be ignored at this point. So R mod I is really the set of all a0 plus a1x such that a0 and a1 both belong to the real numbers. And sorry, I should be very careful, plus I. It's the set of all cosets. Another way of saying that is it's the set of all congruence classes of a0 plus a1x, where a0 and a1 both belong to the reals. Okay, so that's the ring that we're working in. But now, how do we do addition and multiplication in this ring? Well, let's suppose I have two different polynomials, or two different elements of R mod I. So not polynomials, but congruence classes, or cosets. So let's say I have a0 plus a1x, and I'm going to use the bracket notation for this, just so that I don't have to write plus I every time. And I've got b0 plus b1x. All right, so what's that going to be? According to our definition of how to add cosets, that's going to be the same thing as this, a0 plus b0 plus a1x plus b1x. It's the congruence class of that. And I could even simplify a bit by just writing this as a0 plus b0, that's my constant term, plus a1 plus b1x. So that's how we add, and there's nothing that surprising about addition, but multiplication is kind of a trip. So here's how multiplication works. If I want to multiply a0 plus a1x times b0 plus b1x, then I get the congruence class consisting of the product of these, or I shouldn't say consisting of, the congruence class that contains the product of these. Well, what is the product of those anyway? If I distribute, I get the congruence class of a0 b0 plus a0 b1x plus a1 b0x plus a1 b1x squared. Okay, but wait. I know that I can combine these terms, these two in the middle. So I'll go ahead and do that. But then I'm just going to stop for a second and think. I know that a0 b0 plus a0 b1 plus a1 b0 x plus, let's see, that's a1 b1 x squared. That's congruent to a0 b0 plus a0 b1 plus a1 b0 x. Because this term here, sorry about that funny marking on the a, I started to write a b and then corrected myself. But this belongs to I because it's a multiple of x squared, which means these two polynomials, this one and this one, they're congruent mod I. I'll go and write a mod I there, which means their congruence classes are the same, or their cosets are the same. So really, I can just cut this off here. Sorry, put that in blue. There we go. I can cut that off there. That's the product of those two cosets. Again, it's expressible as just a linear polynomial, or a coset represented by a linear polynomial. All right, so that's how addition and multiplication work. Now, here's something kind of twisted. I know that R bracket x is an integral domain. Multiplication is commutative. There's a unity, there's a multiplicative identity, which is just the polynomial 1. And R bracket x has no zero divisors. If I multiply any two non-zero polynomials, each one's going to have a lead term, and the product of those lead terms is going to be a non-zero lead term for the product polynomial. So all that to say, r bracket x has no zero divisors. You should check this and try and prove it on your own, but I'm not going to do that proof in this video. But in r mod I, so this was r was just r bracket x, but in r mod I, the congruence class of x times the congruence class of x again, and by the way, both of those are non-zero elements because neither of these is congruent to 0 mod x squared. The product of those is the congruence class of x squared, but x squared belongs to I, and therefore x squared is congruent to 0. So that makes this a zero divisor of r mod I, which means r mod I is not an integral domain. So that's kind of funny, right? I can start with something that's an integral domain, but by modding out by the wrong thing, or I don't know, maybe the right thing, I get a ring that's not an integral domain. It's still commutative, still has unity, like the congruence class of 1 would still be a multiplicative identity, but I have zero divisors now. Kind of weird, right? Okay, let's do another example. So I'm going to set that over here. So we're going to start with the same ring. The ring of polynomials over the real numbers. But this time we're going to try a different ideal. Instead of taking the ideal generated by x squared, I'm going to define different color now. Let's use a nice green color. J is going to be the ideal generated by x squared plus 1. Okay, different game now. Well, or is it really? I mean, it's possible that by modding out by x squared plus 1, I mean, x squared plus 1 is not so different from x squared. Maybe modding out by x squared plus 1 gives me a quotient ring with exactly the same structure. But I don't know yet, so we're going to investigate. So we're going to ask, what is r mod j? So this time we're modding out by j. All right. So again, let's try just learning a little bit about the elements of this quotient ring. So this time, let's say I have some polynomial, and I'm going to start with a specific example, 7 plus 3x plus 5x squared plus j. Okay, can that be simplified at all? Well, let's see here. I know that 5x squared is equal to 5 times x squared plus 1 minus 5. All right, so what I did there is I just tacked on a 5, so I'd have a multiple of x squared plus 1 here, and then compensated by subtracting 5. All right, but that means that 5x squared is congruent to negative 5 mod j, because this element here, this polynomial, belongs to j. All right, so 5x squared is congruent to negative 5. And because addition mod j is well defined, that's a theorem we proved in a previous video, that means that 7 plus 3x plus 5x squared is congruent to 7 plus 3x minus 5. Or in other words, 7 plus 3x plus 5x squared plus j is the same coset as 7 plus 3x minus 5 plus j. And of course, I shouldn't be coy about this. That's just the same as 2 plus 3x plus j. To put it in congruence classes, that means 7 plus 3x plus 5x squared is congruent to, or is the same congruence class as 2 plus 3x. Okay? So now we have a slightly different structure here, but one thing that is definitely true, one thing I can certainly say, is that, well, so first of all, let's just notice here that x squared is equal to x squared plus 1 plus negative 1. I was going to make an observation, but realized I needed to set it up a little bit better. So x squared is congruent to negative 1 mod j. Now, because multiplication is well-defined mod j, I can multiply each side of that congruence there by x. So I get x cubed is congruent to negative x mod j. Okay, and if you believe that, fine. But if you don't believe that, then just notice that x cubed is the same as x times x squared plus 1 plus a negative x. Okay, so I just take both sides of this equation and multiply those by x. Okay, continuing in this thread, we get x to the fourth is congruent to negative x squared, and the negative x squared is congruent to negative 1 because x squared was negative 1. So that's 1 mod j. Okay, so x squared is congruent to negative 1, x cubed is congruent to negative x to the fourth is congruent to 1, x to the fifth would be congruent to x again because I'm multiplying x to the fourth congruent to 1 by x on both sides. And you could keep playing this game, but the point is, every power of x higher than x, every power of x that's x squared or larger, has a representative that is either a constant or a linear power of x, or a linear term, I mean. So that means that if I have the polynomial a0 plus a1x plus a2x squared plus etc. up to an x to the n, well, that's going to be congruent to something linear. And I'm not going to say exactly what linear thing it's congruent to because it's not this anymore. It's not just a0 plus a1x because these terms are not 0 anymore, but they are reducible to a smaller power of x. Okay, so just to give a quick example, like if I had negative 5 plus 7x plus 11x squared minus, I don't know, 4x cubed minus x to the fourth, well, using the knowledge that I have up here, that's congruent to negative 5 plus 7x minus 11 because x squared is negative 1. And then x cubed is negative x, so I think that's plus 4x. And then x to the fourth is 1, so that's just minus 1, which all of which comes out to, let's see, that's negative 17 plus 11x. Okay, so this polynomial here, if I just set up any polynomial whatsoever, it will be congruent to something linear. Therefore, R mod J is equal to the set of all congruence classes of linear polynomials. And that might lead you to think, well, this must be the same ring as what I had before because it's got the same elements. But being the same ring doesn't just mean having the same elements. It means having the same operations, or at least operations that behave in exactly the same way. And here I claim we are very different. So addition works the same. As in R mod I. Again, you just add constant terms, add linear terms, no problem. But multiplication, very different now. So multiplication in R mod J works like this. If I have a0 plus a1x and multiply by b0 plus b1x, well, at first blush, that's going to give me a0 b0 plus a0 b1 plus a1 b0 x. I'm just starting out the same way because I think the beginning works pretty much the same way. And I've got a1 b1 x squared. But now what happens to the x squared is a little bit different. That x squared is congruent to negative 1. And therefore, I can rewrite this whole thing as a0 b0 minus a1 b1 because that a1 b1 x squared is turning into a negative a1 b1 plus a0 b1 plus a1 b0 x. So that's the congruence class I get by multiplying. And you may be thinking, well, come on though. Maybe this is really the same ring as R mod I that I had over with where I quotiented by x squared, and it's just everything has a different name. Or maybe multiplication looks like it's doing something different, but it's really doing the same thing, just with different elements. But no, I claim this is actually structurally a very different ring from R mod I. And here's how we know. The addition and multiplication we've set up here, and you may have suspected this by now. I hope that you have noticed something about the way this all works. In fact, I may just ask you, if you haven't noticed something by now, like if your brain is not screaming, then look back at what we had up here in this area and see if this reminds you of something, because it should. This element x that we came up with, not the original x that created the polynomial ring, but the x in our quotient, where x squared was congruent to negative 1, and x cubed was congruent to negative x. You've seen that structure before. That structure is the structure of the imaginary numbers. You'll remember that I squared was negative 1, I cubed is negative I, and I to the fourth is equal to 1. So when we say bracket x over here in R mod J, that's really the same concept as I in the ring of complex numbers. So in other words, what we've done here is we've come up with a fancy way to construct a ring that is isomorphic to the field of complex numbers. And this is a field. You can verify every non-zero complex number has a multiplicative inverse. And because it's a field, it is also an integral domain. And R mod I was not an integral domain. So that means R mod J and R mod I are two different rings. So R mod I and R mod J are not just different in name, but different in their ring structure. So that means that we can take the same polynomial ring, R bracket X, mod out by a quadratic. And depending on certain properties of the quadratic we mod out by, we might get very different structures. But mostly the thing that I wanted to do here was acquaint you with the fact that there's a formal algebraic construction for the complex numbers. You may wonder why in the world we can consider a world in which there's a number that squares to -1. And the answer is we can construct it algebraically. If we take R bracket X and mod out by X squared plus 1, well, when you mod out X squared plus 1, you're saying X squared plus 1 is really 0. Well, we really say it's congruent to 0, which means X squared is congruent to -1. And that's how you can algebraically create a square root of -1, even though everything in your brain tells you there should be no such thing.